All right, I want to begin the 2011 questions. So we'll begin with question one. Now, just to be clear, we have a lot going on here. So I just want to kind of take these variables, this kind of variable salad here, and turn it into something useful that we can work with. So this is really an application at first of the impulse momentum theorem. And then what happens is that this projectile gets fired and it embeds itself in a wooden block. So we have to use the work kinetic energy theorem and possibly conservation of energy. So just to start with, we have an impulse, we have a force, we have Vx. So what I'm tempted to just kind of write down is the impulse momentum theorem, just to remind me of what's going on here. So I'll say this is mvx minus 0. The other thing that I'll write down is I'll just remind myself that the impulse is in fact the force times the time. That's what I'm just going to start with even before I begin the problem. So let's see what they want. A, determine an expression for the time required for the projectile to travel the length of the launching device. Well, there we go. Jp divided by F average. All right. Next, an expression for the mass of the projectile. Well, we have this equation that I wrote down above. So the mass is going to be J of the projectile divided by Vx. Perfect. Okay. The projectile is fired horizontally into a block of wood. And the projectile travels a distance d before it stops. Let's get an expression for the work done in stopping that projectile. So what's going to happen is the work done is going to be the change in kinetic energy. So it ends up with kinetic energy of 0. And it starts with the kinetic energy 1/2 mvx squared. But of course we solved for m in part b, sorry. So what we're going to end up getting is the work is going to be negative 1/2 Jp times Vx when we substitute m for m. Lastly, to get the force exerted, well, we know that the work is going to be the force times this distance d. And using this work expression from C, we're going to get the force of the block exerted on the projectile will be force of block equals negative Jpvx over 2d. Excellent. Now, let's just be clear on what values we have and that we don't have. So, in part E, we're going to change the situation a little bit. We're going to take this projectile. We're going to launch it. It's going to hit the block. And then it's going to slide to rest with the projectile embedded in the block. So this distance is capital D. This distance that it embeds itself into the block is d nu. And everything else being equal, let's go ahead and try to solve for some things. So first of all, we want to get dn in terms of all these different variables here. So we're trying to get dn in terms of two different sets of letters. Let's see what we can do. So first, we know that the block starts, the projectile has a speed of 1/2 mvx squared. And all of this got dissipated as work. So we have Fb times d as the work done to slow the projectile down in the first part. So here's what we're going to say. Since this kinetic energy is exactly equal to this work, what we can say is that we have some kinetic energy here that gets turned into dissipated energy at the end. So what I'm going to say is this. I have this E kinetic in the beginning, and that gets turned into, well, we can say two types of E dissipated. There's the E dissipated of being embedded in the block, and then there's the E dissipated of the whole block sliding. So let's try to get both of those. So I know that the kinetic energy is FB times D, and that's going to equal force of the block times the distance, force of the block on the projectile times that little embedding distance. And basically, what we're saying then is that the block slides across the table a short distance d. And here's the thing. The work done there is going to be the force of friction acting over that total distance d in order to stop it. So with all that in mind, I can go ahead and actually isolate my expression for dn as dn equals FB, sorry, this is force of friction, FB times D minus FT times this capital distance D all over FB. All right, so that's part E, and let's move on to part F. Now, for part F, we have to do something a little bit different. So we want to get it in terms of the mass. So let's talk about why we can even use those two masses. So here we go. So we know that mvx of the projectile, we can conserve momentum by saying that is m plus m times capital V for the block. So here's what we know. 1/2 m plus little m times v squared is going to equal the force of the friction times the distance it takes to stop the object. Continuing, we're going to do a little bit of a substitution here. We're going to say that 1/2 m plus m, and we'll do a substitution here of m over m plus m quantity squared times Vx squared equals Ft times D. Now, here, continuing on, there is some simplification that we can do. So one small point. From this point right here, we know that 1/2 mvx squared equals fb times d. So I'm going to do a bit of a substitution. I'm going to substitute vx squared equals f times d times 2 over m into this expression here. And I'm going to actually do that substitution. Now I'm running out of room. But I'd like to see you finish this problem and actually bring that solution to class. I think this would be a great question for us to warm up with in class on Monday as a possible pop quiz that you could do with open notes.